Hi, today's lesson objectives are going to be 1. To find the derivatives of functions including algebraic, trigonometric, and exponential functions. 2. Find the derivatives of sums and products and quotients. And 3. Find second derivatives and derivatives of higher order polynomials. The first thing that we're going to do is we are going to be looking at what a function is and the limits of a function. So let's define a function as f, and so f is the function, and let's define a domain of that function to be in the interval of I. So I can be any value that can go into the function f. And what we're going to be looking at is we're going to look at and we're going to study the concept of the limit of f at a point in this interval, and let's call that a. So we're going to be looking at the limit of f at any point in this interval a, and then in this interval I. So let's see how that looks like in writing. And usually what we write is the limit of the function f with respect to x, and this right here is going to be a subscript as x approaches a. Now what we're looking at right here is we're looking at the limit of this function f with respect to x as x approaches a value of a. There are two ways to look at it. The first way that we're going to look at is as x approaches a, and there's going to be a negative in there. And what that is, this is called the left-hand limit. Left-hand limit. So what you're looking at is you're coming at this value of a in this interval I from the left, and you're looking at the behavior of that function f as the function approaches this value of a from the left. That's called the left-hand limit. The other one that we're going to look at is the limit of the function f with respect to x as x approaches a from the positive values. So that is called the right-hand limit. And in both of these cases, you're approaching the value of a, but you're approaching the value of a from two different sides. So you're looking at the left-hand limit and the right-hand limit of this function of x. And just to give you an example, let's say that we have, let's say, this function right here. That's a function, whatever it is, and we're looking at it from this interval I right here. So these are the values of I. In this interval we have the values of I. And now let's look at a value of a in this interval I. So let's say that the value of a is right here. That's where a is. What you're doing is you're looking at the limit of this function. For the left-hand limit, you're looking at what is happening to this function as the values of a come in from the left, so this way. So what is happening to this function when you look at the value of a as it approaches it from the left hand? And for this other one, what we're doing is we're looking at the value of the function, this function with respect to x, as it approaches it from this right hand side. That's why it's the right hand limit. So we're looking at this behavior of this function as it approaches this limit right here. If the limit of the left hand and the right hand coincide, then we can just write this as the limit as f approaches x, or sorry, the limit of f of x as x approaches a. Since we know that the behavior from the left hand and the right hand is the same, then we can just write it like this. Alright, so now let's look at some properties of limits. And let's start by letting f be a function. So let's let f be a function, and let's let g be a function. And what we're looking at is functions with respect to x. And let's try to look at the limit of both of those functions as the values of x approach a certain value a, whatever that value may be. And the notation for that is going to be the limit of f of x as the values of x approach a. And for the function g, it's going to be the limit of g of x as x approaches a value of a in this g function. So now, assuming that the limit of both of these functions exists, there's certain properties that you have to know of that are really important for finding out how to use this in math. And the first one is going to be the limit of the function f added to the function g, and looking at what happens as x approaches a for both of those functions. And the result of adding these functions and taking the limit of them is just going to yield a result of taking the limit of the function f of x as x approaches a individually, and then adding the limit of g as it approaches x as x approaches a. So that is if you have a limit of two functions that are being added, then they're both with respect to x, then the limit of those functions added as x approaches a is just going to be the limit of f of x as x approaches a, and plus the limit of g of x as x approaches a. So you can just do them separately. The other property, the second property that we're going to look at, is when we subtract two functions. So if you have the limit of f of x minus the limit of g of x as x approaches a, to get the solution, all you have to do is the limit of f of x as x approaches a minus the limit of g of x as x approaches a. So you can just do them separately, just like you did it with the addition. The third property is if you have a real number for a real number, so a number that exists, let's give it a variable of c. For a real number c, let's say that you have the limit, c being a constant, the limit of c, or so you don't get confused, I'm going to put the Greek letter alpha. So I'm going to put the Greek letter alpha so you don't get confused. And what we're going to do is the limit of the function alpha f, and again, remember, alpha is just a constant, and we are going to be looking at x as x approaches a. So knowing that this value is a real number and it's a constant, all that you do is you take out the constant and put it in the front, and then you do the limit of that function with respect to x as x approaches a. Since this alpha is just a constant, you just put it out in the front. Okay, and so now we're going to move on to the next thing, and the next thing that we're going to talk about is the limits of polynomials and rational functions. And there's a very important definition that you have to consider when you're looking at polynomials and the limits of polynomials, and that is if f is a polynomial, meaning that f consists of several terms, then we know that then the limit of f of x as x approaches a value of a in an interval is going to exist. So it exists. So you got if you have any polynomial, you're going to know that the limit as that function approaches as f of x approaches as x approaches a is going to exist, and the limit is going to be given by the limit of f of x as x approaches a is going to be equal to just f of a. So for example, well, we're going to go to examples in a little bit, but that is the definition. So if you have any polynomial, then the limit of that function exists. So that's a very important definition that we have to consider when we're doing the limits. So that's a very important definition that you have to know in order for you to be able to take limits. So if you have any polynomial consisting of various terms, you are going to be able to find the limit of that, provided that there's no funny things going on. Alright, the next thing that we're going to talk about, we're going to look through examples about this in a little bit, but before we do so, we're also going to look at what the definition of derivatives tells us. The definition of derivatives considers this, what we just talked about, the limits, and looks at it from a different perspective. So let me pull this up, and let's say, so suppose you have a function f again. So the function f, and again f is with respect to x, a function of x with respect to x, and it's a real valued function. Then we know that f, so if it's a real valued function, then we know that f prime of x is going to be equal to the limit of f of x minus h minus f of x over h, and now we're looking at it as h approaches 0. This right here is called the derivative of f at x, and this only works provided that the limit does exist. Now, since we know that derivatives involve limits, then we should expect that the rules of derivatives are going to follow closely to what the limit rules we looked at before were. Now again, let's look at two different functions, the function f and the function g again. So those are two functions that are defined with respect to x, and let's say that they're in a common domain. One of the rules that you guys have to know very closely for these derivative definitions is one that is for the sum of functions and taking derivative of that sum. So we're going to write that as d over d of x. The derivative is with respect to x of the function f of x plus g of x. And the derivative of that function is just going to be the derivative of the function f of x plus derivative with respect to x of the function g of x. So if you have two functions that are being added and you take the derivative of those two functions that are added, you can just take the derivative of those functions separately. The second one that we're going to look at is the difference of two functions. Difference the difference of two functions. So if you have, again, d of x, the function of f of x, minus the function of g of x, as you would expect, you take the derivative with respect to x of the function f of x and you subtract it from the function g of x. Okay, so that's the difference rule. Now the next one that we're going to look at is the product rule of the product of two functions. And so if we have the derivative with respect to x of two functions, f of x times g of x, it follows a very specific rule. So what you do for this types of functions is you take the derivative of the first times the second, and then the derivative of the second times the first, and this is how it goes. So the first is this function right here, f of x. So we're going to look at the derivative of the function f of x, and that is going to be multiplied times g of x. But just g of x, not the derivative of g of x. And then we add the function f of x times the derivative of g of x. So this is why a very useful thing to remember when you're looking at the product of two functions is you take the derivative of the first times the second, and then you add the derivative of the second times the first. So that's a very important rule, and this is referred to as the Leibniz rule. The last rule that we're going to look at is the quotient rule. Also a very important rule to remember. Let me get some space here. So this is going to be the derivative of the quotient of two functions defined as the quotient rule, but you have to know that this can only be done whenever the denominator is not 0. So this is only going to be able to be done whenever the denominator is non-zero. Okay, so then how we write that is if we take the derivative of a function with respect to x, and what we have here is we have a quotient f of x divided by g of x. So we're taking the derivative of this function, and it has a very specific definition that is related to the product rule, but a little bit different. So try not to confuse both of them. And what we have is, again, the derivative of the top so you can consider that the first times the second, again, and then we subtract. So just pay attention to that, because before, when we did the product rule, that's addition. We're looking at subtraction for the quotient rule. And again, the derivative of the second times, well, that would be the first, but then this is the derivative of the second. And to that, it's going to be divided by the original g of x squared. That is the quotient rule. In the following minutes, we're going to look at a couple of examples that show you how we use these definitions to find the derivatives and limits of different functions. So let's look at our third example, and let's think about the rules that we learned about limits previously, and we're going to try to use those rules to evaluate the limit of these two functions as x approaches 2. Okay, so this is what we have right now, and we're trying to see what happens to this difference of functions as the value of x approaches 2. So because we know that the limit when we subtract two different functions is just the limit of them taken separately, what we can do is we can just look at the limit of each of these separate. The problem with this is that we won't be able to know the limit of this function because x cannot be 0. Or sorry, the denominator cannot be 0. So for example, if we put right here 2 into this function, it's going to give you 1 over 0, which is undefined. So what we need to do is we need to figure out a way to simplify this function, this combination of functions, so that we can take the limit as x approaches 2. So what we're going to do is we're going to look at all of these functions and see if there's a way to simplify it. The one that I see can easily be simplified in this example is this value right here. So if we take a look at this right here, x to the third minus 3x squared, you can see that it has that each of these terms, this polynomial has a term that they all share, and that is x. So let's take that out of the function to see if we can simplify it a little more. So the limit as x approaches 2 of the function, so this can't be simplified, it's already simplified. The top is also already simplified. And now here we can simplify by taking out a value of x. Now when you take the value of x, what you're left over with is x squared minus 3x plus 2. Right? And this right here is also a polynomial that can be simplified. This is just a quadratic function. So how we simplify that is if we just do it together, so we have x of x and x, so we can get this x squared. Now we need to find a value that multiplies to 2 and also adds to negative 3. The combination of that is going to be negative 1 and negative 2. So that is going to be our simplified function, x minus 1 and x minus 2. Right, so we simplified this to see if we can simplify this combination, this difference of functions any further. Now something that you can see right here is that we have a value of x minus 2 on both of these denominators. Now what we're missing from this function right here so that we can make the denominators equal is we are missing this part from this function. So what we're going to do is we're going to multiply the top and the bottom, therefore creating an equivalent fraction, therefore not changing the value of it. So what we're going to do is we're going to multiply the top and the bottom by x minus 1. Let me put that x minus 1. And we have the x minus 2 that was originally from there. And this one, since now we have equivalent denominator, we're not going to do anything to this one. Now that we have two equal denominators, now we know that if the denominators are equal, so let me just give you an example. If we know that the denominators are equal in a fraction, then we know that we can just add the top, so 2 plus 1, and it goes over the same denominator. So we're going to do that here. We're going to use this rule, the simple rule, to simplify this. So now that we have equivalent fractions, now we can simplify this to, and if we multiply this out, combine all like terms, we know that the denominator is going to be x minus 1, x minus 2. Once we combine all these terms right here in the top, we should get a value of x squared minus 5x plus 6. Now we know that that x minus 2 cannot equal to 0, right? Because that would make this function undefined. So let's simplify this top a little bit more. And we can simplify, since it's a quadratic, we can simplify it into two terms, x minus 2, x plus 3, and the denominator is the same. And this is very useful right here because now we can take out this original, this value that would otherwise make our function undefined. So because we know the top and the bottom share the same common factor, we can eliminate that. And what we have is x plus 3 over x minus 1. Oh, and I'm sorry, right here I made a mistake of putting plus. That should be a minus. Right, yeah, because 2 times negative 2 times negative 3 is 6, yeah. So it should be a minus right here. Okay? And again, we know that x minus 2 cannot equal to 0. Now, since we were able to eliminate this this term that would have otherwise given us an undefined solution, now because we have gotten rid of that x minus 2, we can now take the limit of this function as it approaches 2. So again, we have two functions, and for this we're going to be looking at what happens when we divide two functions. So all that means is that when you divide two functions, you just look at the two functions separately, and then you divide them, and that should give you the answer. So if we are to look at the limit of these two functions, all that we have to do is we have to replace this 2 minus 3, because that as x approaches 2, and then 2 minus 1. And again, I just want you to keep in mind that this is where dx was before, so we just replace it and we look at what happens when we now have that. So as the limit of that original function as x approaches 2 is going to be 2 minus 1 minus 3 is negative 1, and then if you multiply 2 minus 1 is 1, 1 times 2 is 2. So the limit as it approaches 2 of that original function right here is negative 1 over 2. Again, to summarize, that's how limits work. Using the properties that we learned, what we do is we try to simplify the two functions in a way that allow us to replace this value of x, and making sure that when you replace this value of x2 into these functions, that there is no strange solution or value that is going to give you an undefined equation. So if we would have started with 2 and putting it into here, then we would have had 1 over 0, which is undefined, and it wouldn't have allowed us to find the limit. So whenever you have these types of complex polynomials, there has to be a way for you to simplify the values and see if you can eliminate a term that would create a problem for you, as in this one, in this case. And by manipulating these functions, you can work so that at the end, when you replace the value of x into the function, you will have a limit of that function, a specific value for the limit of that function. In this case, it was negative 1 over 2. All right, let's look at example 2. In example 2, we're going to look at derivatives. So, oops. All right, so example number 2. And in example number 2, we're going to tie together what we learned about limits and derivatives by first finding the derivative of find the derivative of the function f of x to the third. And we're going to start by looking at how we can look at how do we find derivative using limits. So what we're going to do is find the derivative of using A, limits, and B, the definition of derivatives. Okay, so this is our function right here, f of x, and that's equal to x to the power of 3. So now let's look at, we started out with the definition of limits right here. Where is it? Right here. So we knew that when we're doing the derivative of a function f, the derivative of that is going to be equal to this. That's the definition. So let's go back right here and let's look at the f prime of x. So the first derivative of x of the function f with respect to x, and that is using the definition is going to be the limit as h approaches 0 of f of x plus h minus f of x all divided by h. That is the definition that we defined at the beginning when we were talking about limits. Okay, so now let's use that using that definition we can find the limit of this function. So that is going to be equal to the limit as h approaches 0 of, so we have x to the third, so it's going to be x plus h to the third minus the original function x to the third divided by h. So in this one, all you have to do is add h to the function to x, and that will give you the function of f as x plus h. Okay. Now what we're going to do is we're going to try to simplify this again, so that we can get rid of this h that is going to give us an undefined solution, because we know that h cannot be equal to 0 again. So we're going to try to manipulate this so that we can actually find the limit of this function. So we know that x plus h to the power of 3 is going to yield, if we multiply it all out, if we were to do x plus h to the power of 3, which would be equal to x plus h times x plus h times x plus h. I'm not going to go over the multiplication, but what you should be able to get is x to the third plus h to the third plus 3x h x minus, plus h. So if you multiply this out, this is what you should get. So now we're going to replace that into our original function, and what we have is, again, x to the third plus h to the third plus 3x times h times x plus h. And let's not forget that we had this term right here, minus x to the third all over h. Now you guys can easily see here that one of our terms gets eliminated. Positive and negative are going to get eliminated, and now we're left over with this. And we're lucky because in this case, each of these terms has an h. Now if we eliminate one of those h's, what we're left over with is the limit as h approaches 0 of x squared plus 3x x plus h. And since the h gets eliminated from on the top and on the bottom, this is what we're left over with. Now that we can replace this value as h approaches 0 into h, we should be able to get a value. So if we put 0 here, this is going to get eliminated. So this is going to be equal to 0. This is also going to be equal to 0. And what we're left over with is 3x times x, which is going to give you 3x squared. Okay, so that is how we find the derivative of a function using limits. Now let's try to see if we can use the definition of derivatives to be able to do this. So this was our definition of the derivatives, and so what we're going to use is we're going to use this notation now for part B. So for part B, we're looking at the function f of x is equal to x to the third. I'm going to do it in different colors so that you guys can look at different. Okay, so now let's look at this. And what we're doing on this one is we're taking the derivative of the function. So derivative with respect to x of x to the third. So we can find, so that's using the definition of derivatives. And as you will practice and learn throughout the rest of this course, is to find the derivative of a function. You take the exponent, you bring it down to the forward, and then you subtract this minus 1. You subtract the original value of the function minus 1, and so that works out because you guys can see that 3 minus 1 is going to be 2. So the derivative of the function x squared, x to the power of 3, if we use the definition of derivatives, we should get 3x squared as we did with limits. And don't worry, we're going to look at it a little more, a couple more examples dealing with this. Okay, so now let's look at how we can just use, instead of using limits, we're going to just use derivatives to be able to find the values of how to evaluate functions. Okay, so this is example number 3, and we're going to find the derivative of 2x to the fourth plus x. Okay, and in this case, let's let y equal to 2x to the fourth plus x. Y be used, y is interchangeable, right? F of x, y is the same thing as f of x, but in this case we're going to use y so that we can simplify the notation for derivatives. So in this case, we're taking the derivative with respect to x of this function y. How we write that is going to be the derivative of y with respect to x is going to be d of x of 2x to the fourth, and using our rules, this is the sum rule that we looked at before, we can take the derivative of both of these functions separately. Okay, so now using the what we've learned about the derivatives, we can simplify this a little bit further. So the derivative of that function is going to be equal to, again, so we're going to put this 4 in the front, so it's going to be 2, that was already there, times 4 x 4 minus 1. So you take this, again, you take this exponent, you put it in the front, and then you subtract 1 from the exponent. We're going to do the same to this one, and this one has an invisible 1 in the middle, in the front. And so we take this to the front, so it's 1 x and then 1 minus 1. If once we simplify this, we have 2 times 4, which is 8 x to the third plus 1 x to the 0. We can simplify this a little bit further by realizing that anything to the power of 0 is 1. So what we're left over is that the derivative of y with respect to x is going to be 8x to the third plus 1. Therefore, now we can go back into our original function, and we know that the derivative with respect to x of that function that we were given, 2x to the fourth plus x, is equal to 8x to the third plus 1. That is our solution. And let's just remember that this right here is an example of the sum of two functions. So you can do them just separately and just add whatever it is. So that is the same thing as or is equivalent to also subtracting it. So if in this case that we did, there was a minus here, it would just, the answer would just have x to the third, 8x to the third plus 1 minus 1. So this can be used as an example for the sum and difference So I guess I can just copy this so you can, this right here. So this is an example of the sum of difference of That's an example of the sum and difference of two functions. Now let's take a look at another example. We're going to look at this example, and in this example we're going to look at the product rule of derivatives. And if you have not seen how to take the derivative of cosine, you should be able to get some practice later. But in this case, we're gonna see how we can use that definition to find the derivative of this function right here that is made up of these two functions that are being multiplied, x squared times cosine x. And what we're going to do is we're going to let y equal to x squared cosine of x. And again, just like how we started before, we are going to look at the derivative of y with respect to x, and that is going to be the derivative with respect to x of x squared cosine x. And again, now we're going to use the product rule. So we know that we can just look at the derivative of the first times the second. So that's what I'm going to do. I'm going to do d of x squared times cosine of x plus, since we're doing multiplication, and it's the derivative of the second being cosine x. And let me number them so that you may have a better understanding. So the first I'm going to put right here 1, and for the second I'm going to put here 2. So we're doing the derivative of the first, which is x squared, times the second, and then we're doing the derivative of the second times the first. Okay? And using what we have just seen right now, it should be bring this 2 down to the front, subtract 1 from the exponent after you've done that, and we're going to multiply that times cosine of x, plus this stays by itself. And if you have not seen the definition of derivative of, so whenever you have d of x, the derivative of cosine of x, you should know that that's just a trigonometric rule that you're going to learn soon, and that's going to be negative sine of x. So then it's going to be times the negative sine of x. So that's just a rule that that you should be able to memorize, and they're very important rules to memorize. So now let's simplify this, and we have 2 times 2 minus 1 is 1. I'm just going to leave that 1 out because it's implied if it's not there. Times cosine of x, and we have minus x squared sine of x. And again, what we're doing right here is we are using the definition right here of the product rule, where you take the derivative of the first times the second times the derivative of the second times the first. Alright, lastly we're going to look at the quotient rule and something called the chain rule so that we can have a better understanding of how this works. Alright, so now we're going to find the derivative of this quotient, 4x minus 2 divided by x squared minus 1. Now let's look at this. So we're going to let y equal to 4x minus 2, x squared minus 1, and then we're going to take the derivative of y with respect to x. So derivative with respect to x is going to be equal to 4x minus 2. Okay, so in this case we have a quotient, and we have a very specific rule that we use whenever we're doing the derivative of quotient, and I'm going to copy it so that you may reference it as we do this problem. Alright, so we're going to be using this very closely. Alright, so going off of the definition of the quotient rule, we should be using this. So again, I am going to number these so that you can see the difference. So let's call this top one the first, so 1, and the bottom one the second. And I'm going to put it in different colors. Top is the first, bottom one is the second. What we're going to do is now we're going to take the derivative and follow this definition very closely. So to take the derivative of this function, we are going to do this right here represents the first. So we're going to do the derivative of the first. So we have 4x, there's a 1, so I guess so that this may be facilitated, and I'm going to do every single step. So 4 times, let's see, the derivative of x, it has a 1 right here, so that you bring down the 1, and then subtract the 1 from the exponent. Okay. And since this one has no x, this constant is going to be 0. So whenever you have a derivative of any constant, it's always going to be 0. Constant mean any real number. that doesn't have a variable. So minus 0, so that's the derivative, times x squared minus 1. So the derivative first times the second. So let's simplify this a little bit. Actually, let's save the simplifying until after we're done with this. So now we subtract it from f of x, which we know is 4x minus 2, derivative so the derivative of the second times the first. So this is the first times the derivative of the second. So just see. So we have, again, we have x squared, so we have 2x, 2 minus 1, minus, again, derivative of any constant is 0. And all of that is going to be divided by g of x, which is the second, squared. Now let's simplify this. So we have right here x, 1 minus 1 is 0. 0, any number, any base to the power of 0 is always going to be 1. So then we have 4 times 1 is just 4. X squared minus 1 minus, right here we have x minus 1, x2 minus 1, which is 1, so it's going to be 2x, multiply times that. So I'm just going to bring the 2x to the front, multiply times that. And right here we have x squared minus 1 squared. We can simplify this a little bit further, and we have, what we have is 4x squared plus, sorry, and so what we have right now is we have 4x squared minus 4, multiply all that out. Now right here what we have is 8x squared plus 4x, all divided by x squared minus 1 squared. Putting this all together, what we end up with is 4x, we combine the like terms, so we have negative 4x squared plus 4x minus 4 over x squared minus 1 squared. Now, seeing as though we can't simplify this any further, even if we take out a 4, we still have pretty, or actually, let's try it. Let's see. So we take out the 4, what we have is negative x squared plus x minus 1, all divided by x squared minus 1 squared. Now you see, there's this can be factored. So what we're gonna we can only leave it as this. So the derivative. So what we have is that the derivative with respect to x of that function that we started with, which was 4x minus 2 over x squared minus 1, is equal to this value right here, since it can't be simplified any further.